Cool. Okay. Let me share screen. Okay. Can you guys see my screen?
I cannot.
Let's see.
I cannot either.
I can only see a black void.
Okay, that's not a good sign. Let me connect it up. Something else. Which battery do I have? Okay. Yeah, give me 1 second. I gotta connect my phone manually. Okay. Yeah, so today I wanted to talk about really the bulk of the class, which is going to be on how do I deal with integrals in a general sense. Like most of the time, these problems are, let's see. Okay, can you see my screen now? Okay, great. So yeah, we talked about measure theory. There's one thing I put up, I'm going to put up lecture notes, update lecture notes today, but I just wanted to show you guys what Vitali's covering theorem was. So I mentioned it last time. Basically, all it says is if I have a collection of like a family of spheres, then I can make them somehow countable and disjoint up to sacrificing a factor, right? And that gets you, it's somehow a reduction of going from like an infinite collection of things to like a countable collection of things. So it gets you, and then I can measure this countable collection. And then the thing out for that problem we mentioned last time, you can use this idea of like for every open set, I somehow can find a collection of disjoint closed balls, all with bounded radius, such that I can perfectly approximate my set U, right? So these two things are kind of related, and it's kind of like this idea, you know, in topology where you can write any open set as being the infinite union of balls in the metric. This for measure theory, that's not enough because I need it to be countable. So this is somehow like reducing it to a countable situation. Okay, so I'll put those up if you wanted to read them. They're more advanced things, but still useful to know. Okay, so let's go to the new stuff. So we talked about measurable functions last time, how to converge and measure. Talking about measurable functions, how they're like almost indicator functions. Igorov, which shows that measurable families of functions are almost uniformly continuous. Lucen's theorem, which says that, okay, I'm almost continuous if I'm measurable. So I can always restrict to a subset, and in the subspace topology, I'm continuous. And then finally, last time, now we're going to talk about integration. So like, how do I actually use these things? Okay. The first thing, which is like kind of fundamentally important, is Chebyshev's inequality. So it relates, how do I think about the super level set of a function? And how do I relate it to the integral? So like geometrically, I like thinking about it like this. So let's say I have some level alpha, and I have some function like this. This is f of x. This is my set E. And so this set here is going to be all of these points. So I look at the places where I'm above this point, and I pick out the set in E where that happens. So this is the thing. Something like this, right? So these sets are the ones that satisfy x and E, and f of x greater than or equal to alpha, right? And what it says is, okay, I can bound this by 1 over alpha times the integral over the whole thing, right? So the right-hand side here. Does anybody know how to prove this?
I think you just take an indicator on that set, and it should be less than the function itself.
Sure. Yeah, yes. So let's do that. That's exactly what it is. So generally, so like proof, the way I like to think about it is I integrate over this set, It's basically what you were saying. But I look at my function f of x dx, right? And so what I know actually on this set is this condition, right? So I know below, I can bound it from below. This is a positive quantity. The integral's kind of monotone with respect to inequalities. So I know that this is bounded below by the same set, so x and e, such that f of x is greater than or equal to alpha. But I just put an alpha here, right? And so this is going to be exactly alpha times the measure of this set. So this is the indicator you were talking about, such that f of x is greater than or equal to alpha. And then to kind of complete the proof, as an upper bound, this guy is less than or equal to, well, this function is positive. And if I remove this condition here and just integrate over e, I only get more points. So this is going to be the integral over e of f of x dx. And so that completes it if I just look at it backwards. So really, it's kind of like a lower bound. I like viewing it as a proof of a lower bound. Yeah, any questions about this? So proof pretty clear? All right, perfect. So that's Chebyshev's inequality. Different people write it different ways, by the way. So you might see this written a bunch of different ways because the how do I say this? The way you spell Russian names is not consistent. There's different ways to write it. Okay. The next fundamental thing is Fatou's lemma, which holds in a very, very general sense. So one of the most important things to know is when I do Fatou's lemma, I have to pick a sequence of positive functions. Otherwise, this theorem doesn't make any sense. Then what we can do is we take the lim-imp of our sequence. So this always exists, right? And we can take it outside of the integral and giving up mass, right? So what's happening is I can always somehow, like when I pull out a limit out of my integral, right, I get bigger, right? So this always works for positive functions. And it even works if the left-hand side is infinite or the right-hand side is infinite, right? So this works in the extended sense. Okay. Can anybody, so, okay, as like an exercise, let's look at, so when does this fail? When is left-hand side not equal to right-hand side? So in other words, can I construct something, for example, where this guy is 0, just the left-hand side is 0, and the right-hand side is like 1 or something? Do you guys, can you think of, anybody think of an example where this happens?
Yeah, sure. You could take an indicator on n to n plus 1 and just slide it over.
Yes. Yeah, that's perfect. Yeah. So example here would be n plus 1 of x, right? And so when I take the lim-imp of this quantity, so I look at the left-hand side before integrating fn of x, because it's sliding right, this interval, so it's like 1, and then it keeps sliding right. For any point I pick, so I pick an x, for a large enough n, it will leave that point, right? So the interval will escape past that point. So this is going to be 0 always. So when I integrate this, it's going to be 0. For the right-hand side, what do I have? So I know that, well, I integrate, let's say e is r. So when I integrate this guy, this is always going to be 1. n plus 1 x dx, this is 1. So when I take the lim-imp of it, I get 1. So, okay. And this is generally what happens. In some sense, this theorem works for when I'm escaping to infinity somehow, like left and right is the way I view it. So for these types of theorems, you'll see there's 2 types of behaviors which are trying to control. One is if I'm sliding out to infinity, if I'm losing mass out to like spatial infinity. The other is if my function actually devolves and goes to infinity, right? So all of these theorems we'll talk about, either I need some control on positivity, so it's a lower bound, and I get inequalities, or I somehow control all of the behavior. So this is what you'll see in dominated convergence. Okay, well, let's move on. So this is Fatou. There's a version for lim soups, which some people call reverse Fatou, but generally you can deduce all of the things you would like from just this statement, Fatou's lemma. Okay, so let's go next. I'm going sequentially through how integration theory is taught, basically. So the first thing you always prove is, okay, what happens for positive functions? In this case, we're trying to categorize what happens when I have positive functions which are increasing. So what this means is I have fn is strictly less than or equal to fn plus 1, right? For almost every x. And they're positive, so these are all positive. In this case, regardless of whether the integrals are finite or not, I know that I can commute the limits and the functions. So this guy is going to be the limit as n goes to infinity, fn of x. So I'm allowed to commute if I'm positive and I'm increasing, right? Okay, and so this one's super fundamental. There's not really much more I can say about it, I'll be honest. The next one is actually when I remove this condition of increasing, right? And so I have to assume two things. Let E, so the set I'm integrating over, be finite. And if I take a sequence of functions which are uniformly bounded by some constant m, and they converge to each other almost everywhere, then I can commute the limits and the integrals, right? And really the thing we're trying to avoid here is somehow a scenario of a function that blows up like upwards, right? So I'm kind of bounded between these guys. So this is my set E. And as the last example with the sliding interval, right? I could push it out to infinity. For this, when I'm bounded in a finite measure sense, I'm somehow in a ball and I can't push things out to infinity. The other bad thing that could happen is if I push things upwards. So as an example, consider this function. So if I let fn be the characteristic function where this is 1 over n, this is of height n, right? So this is f of x, this is x. So f of x, fn of x is equal to this guy. So it's this integral from 0 to 1 over n times n. And so this is not a bounded sequence, right? So for any positive number, I can always escape past it. And when I take a limit as n goes to infinity, fn of x, what is this? So if I'm away from 0, what happens? I'm 0.
It's 0.
Right? Okay. If x is not equal to 0, and if I'm 0, what happens? I'm positive infinity, right? If x is equal to 0. But this is a measure 0 set. So the point x equals 0 is measure 0. So really this guy is equivalent to 0 in L1, right? When I'm looking at things modulo almost everywhere equivalence. So f actually the limit is identically 0. But the left-hand side, when I integrate this guy, integrate fn of x, this is always going to be 1, right? Because I'm just measuring the area of this rectangle. So this is one of those examples where it's like a fundamental one to remember why I need boundedness. If I'm allowed to blow up, I cannot commute the limit in the integral, right? I still get things like, this is still the scenario for like this theorem, right? I can still apply Fatou in this case, but I just can't say that the limit is equal. I just get a less than or equal to. Okay, anybody have any questions about this, about bounded convergence? Okay, wonderful. So the next theorem is really the big hammer of this kind of area. So dominated convergence. It replaces this idea that, so for bounded convergence, I somehow restrict myself to being in a box, right? So this is of size M and this is like R, right? And so I look at functions which are kind of restricted to here or lie below in this box. For dominated convergence, this is somehow the more general version of like what this box idea means. It just means that in general, I have some L1 function. So I think of G as like this L1 function on RD. And as long as my behavior, as long as my sequence of things stays below this point, I know that I can commute the things. So if I read through the theorem, let Fn be a sequence of L1 functions, which converge almost everywhere to F. And if there's an integrable function G, so it's this G here, such that Fn lies less than or equal than G. So I'm within this, I think of it like an envelope for every single N, then I can actually commute the integrals and the limits, right? And so somehow it takes care of both this thing of if I have an infinite domain and arbitrarily high in some sense. So G doesn't have to be finite valued. It can be infinite at certain points. And I'll still be okay. Okay. So yeah, this is somehow the most general theorem I think you'll be using frequently if you continue in analysis. Okay, so theorem 17, dominated convergence. The next one is a
Can I
very,
ask you a question?
yeah, go for it.
So the boundary convergence theorem is just a special case of the dominating convergence theorem. There's nothing more to it, right?
Exactly. Yep.
Yeah, okay. And why we have two?
In some sense, I think it's I did it pedagogically. When you prove bounded convergence, you end up using bounded convergence to show dominant convergence.
Okay.
In some ways. Yeah. So it's like it's the natural progression. You can kind of see it, right? Like it's kind of this is the base case scenario. I've reduced it to where I'm just like everything's bounded behavior in some sense. And dominated convergence is when this is somehow the scenario where it's the most general where I can still reduce it to this case. There's an argument which allows me to kind of reduce it to this case. So I've included it just because this is the thing you end up applying, but the picture I have in my head a lot of the time is this simpler thing.
Thanks.
For sure.
Wait, how do you prove this with bounded convergence? I've only ever seen it with Fatou's lemma.
Let me think. So the way I want to say you can do this is because if I have Fn is bounded by G like this, my mass cannot be escaping to infinity. So what it means is I can restrict to a ball of radius r for some arbitrarily large r, such that my integral outside of that ball is small, right? So you give me an epsilon, I can find a ball of a huge radius such that if I just look at the problem on a ball of huge radius, then I'm good, right? So that's one reduction you can make. I sacrifice an epsilon, but it doesn't really matter. For the thing where I'm being bounded above, right? I know that an L1 function cannot be infinity too frequently, right? If it's integrable, I cannot be infinity too often, right? And there's a more quantitative version you can say where I give up some small epsilon and then I have to be somehow like below a certain line. So in some sense, that's how I'm reviewing the reduction. Is it's just I have this general scenario. I give up 2 epsilons. It's a 2 epsilon argument to get back to bounded convergence, and then I prove bounded convergence. Again, I don't know if I haven't read the theorem in a long time. That's the way I would try to do it. It might be more technical than that, but I think you get the idea of like.
Yeah, that makes sense. Thank you.
Okay.
And this works in any measure space, right? Not just R to the D.
So that's a technical question. So I think it works for the space of Radon measures, which are compactly generated. But like, yeah, you shouldn't really have to think about, basically, Lebesgue measure is the stereotypical thing which you'll be thinking about for this anyway.
But your argument should work for any sigma finite
Yeah,
space. And then once we know it works for any sigma finite space,
Mhm.
then we can do this trick where we take the set of all x such that g of x is not equal to 0,
Mhm.
and that will be a sigma finite space, and then we can restrict our analysis to only that space. So it should work for any measure space.
Yeah, in general, this works for a measure, right? It's just I don't want to say anything false, so there might be some conditions on the measure. But I think, yeah, sigma finiteness should be okay for this. Yeah, for exactly the patching reason. Like I want to somehow reduce from this case to this case. Okay, I got one more question. This one's a big theorem, so if it's like mystical still, like okay, it seems pretty good. Okay, so here's before we go on, there's a generalized version which I wanted to show you. But before that, let's talk about Jensen's inequality. So this has to do with how the integral behaves under convex functions, right? So a convex function, if you recall, so phi going from, it's just r to r here, r to r is convex if the following holds. So if I have any 2 points, so I have an x1 and an x2, and I look at their linear interpolation, right? So t is in 0, 1. So in some sense, what I'm doing is I'm having 2 points, x1 and x2, and I'm drawing the line in between them, right? And what I want for a convex function is that this is less than or equal to somehow the line between the 2 points. So x1 plus 1 minus t phi of x2. Right? And so what this would mean is for every 2 points, I want my function to be below this line if I was to look at this inequality. Right? So that's what convex means. It's like going upwards. It's a little more general a condition. This doesn't have to be continuous, for example. So this phi doesn't have to be continuous. But if you wanted to look at convexity another way, you could say that the second derivative is positive, right? So if I take a C2 function whose second derivative is positive, this condition always holds. And what it says is on the left-hand side here, if I look at the average of a function over some set E, then when I take my quantity phi of it, I lose a little bit, but I can put it inside the integral, right? So I can start doing pointwise things. So an example of this would be taking phi of x equals x squared. Phi of x equals x squared. And this gets you that, okay, if I take, for example, the integral over the ball of some function dx, and I square it, this is going to be less than or equal to 1 over b squared. Integral over the ball of f squared, f of x squared. Okay. Okay. So yeah, any questions about this?
Yeah, I think convex does imply continuous, but not necessarily differentiable.
It depends on the set E.
Oh yeah, well for R.
Yeah.
Because phi is just a function from R to R. So phi
Yeah.
being convex doesn't have anything to do with E.
Yeah, I'm not sure exactly at the moment. You might be able to take a derivative somehow in this equation. But when I say convex, all I mean is this, right? And if I'm twice differentiable and my derivative is positive, I can show this property. You might be continuous, but I'm not sure. Anyway, those are things to look up later if you need it, right? Like extensions of Jensen's inequality. Okay. Okay, let's move on. So this one it's got a star, so it's not strictly needed in the exam, but it's like the most general version of dominated convergence. I've found that's useful for problems. So what it says is if I let Fn be a sequence of L1 functions, right, that don't have to be necessarily uniformly integral, right? Or they don't have to be bounded in L1. And I let Gn be another sequence of functions such that I get a uniform bound, right? So Fn is bounded by Gn. Gn converges to an L1 function G, and somehow dominated convergence holds, right? So in some sense, what I'm saying is assume I'm looking at dominated convergence, but instead of one envelope, I have a series of envelopes, and the series of envelopes holds with like dominated convergence holds for them. So the integrals converge. Then in that situation with this family of envelopes, I can say that the limits commute, right? So the integral of Fn, and I take the limit of that, converges the integral of F. So this is just something to be aware of. You can generalize to this case where I have a sequence of envelopes instead of a single one. Okay. Okay. Any other questions about integration theory like that? So commuting integrals and limits. Okay. If not, let's go on to LP spaces. So just to recall, I have a function f as an LP of, let's just keep working in RD. And the way you define it is you just take the pth power. RD. And the reason you put a p here is you want to make this a norm. So in general, this space LP of RD is just to be the set of functions going from RD to R bar. So they could be positive or negative infinity. That's what this bar means. Such that the LP norm of F is finite. So this makes LP of RD with this norm LP of a norm space. So there won't be so much functional analysis, but it's kind of good to think of this, you know, function like as a functional analysis sometimes. Like, okay. Yeah, and in general, I think the way you should think about LP spaces, so for P in 1 and infinity, somehow it measures how much of my mass is concentrated away from infinity, right? In a really kind of general sense. So you get more qualitative information by taking LP norms of functions, right? So often you'll see in, for example, in dispersive PDEs, if you end up going to dispersive PDEs, they end up defining these funky spaces that are kind of LP based, just so I can play around with this parameter P and get some more control about my functions. Okay, so let's talk about generally what theorems I can say. So first we need a definition. So I'm sure you guys have seen this before. If I take 1 less than or equal to P less than or equal to infinity, I can define a P prime, which is the conjugate of this exponent. So what it satisfies is 1 over P plus 1 over P prime equals 1. So often when you see people playing around, there'll be things where you want mappings between LP spaces. And people will draw a diagram in terms of 1 over P for this reason. So you'll end up seeing things of diagrams that look like this. So there's maybe 1 over Q. So you'll see this in if you work on nonlinear Schrodinger, you'll see pictures like this of, this is somehow like, if I'm in this point, that means I'm a continuous mapping from LP to LQ. So some people call it, this is like the functional and analytic playground. So if I can do some argument with these exponents, I get information. Okay. So this is just the definition of conjugate exponent. The way you end up fundamentally using this is Holder's inequality, which says if I take any P, I can look at its P prime, and I can integrate the product and write it as this product of norms, right? And if you guys wanted to, as a little quick check, you could prove this. The reason I have this condition is I can write 1 as 1 over P plus 1 over P prime. So that's really kind of the basis of why I want over P and 1 for P prime. Okay. So yeah, I'm not going to go through the proof. Sorry, 1 second. I'm going to pause share. So sorry. Okay. I got some mail. Okay, that's Holder's inequality. Next is a fundamental one, which says that this is actually a norm. So I have triangle inequality on LP spaces. And this can be proven using basic methods. So I think you should just remember this. So whenever I take a norm of something, I should be able to pull out the norm with respect to addition, right? This is all familiar to you guys, right? Okay. So this is Minkowski. I'm not going to go through the proof. The other one is what I call reverse Holder. I'm not sure if that's standard notation like name or not, but what it says is I can characterize the LP norm of a function by looking at the integration against functions in LP prime, right? So this implies, or you can think about this like the norm. So if I look at a G in LP prime of RD, what this does is this induces a mapping. I'm going to call it F of G, which goes from LP of RD to R. And the way it's given by is F of G of some function F is just going to be the integral of F times G dx. So what this theorem says is that the operator norm F of G as an operator between the space let me think, on LP of RD star, so the dual of this space is going to be equal to G in LP. Right. Okay. So what this says is LP RD, the dual of it is going to be LP prime. These are isometric. So this is the functional analytic way to view it. I can measure things in LP, and I can do this. One of the things though is there's some argument that fails for. So here I need P in between 1 and infinity, but not including infinity. But this theorem works in general. Okay, so the way I would categorize how you should think about this is if I ever have a problem where I'm asked about the LP norm of a function, sometimes what I can do is it's easier to look at it as just integration against another function, right? So what you can do in proofs, for example, control the LP norm in some way. What you can say is you can use this theorem to, you give me an epsilon, I can pick something which approximates this LP norm up to an epsilon by just integrating against a G. Okay, so this is what's called reverse Holder. Yeah, and then this is LP duality. I guess this is what I was saying before. So if I let 1 be less than P, which is less than infinity, then if I take the dual, wow, if I take the dual of LP, I get LP prime. So, and as said another way, for any continuous linear map from LP to R, I can get a function in LP prime such that this linear map evaluated against a function in LP is just integration against this function G, right? So this is the notation I was using before. Okay. So let's keep moving on. Yes, okay. So what's very nice about this kind of like dual perspective on LP is I can define a weaker notion of convergence than convergence in norm, right? So the definition goes as follows. I somehow lift my scenario to being, instead of caring about things just on LP, I somehow care about the dual. So if my dual can pick out whether I'm converging or not, then it's a type of convergence. So we say a sequence Fn is an LP converges weakly to F in LP for 1 less than P less than infinity. And we write it as like the same as the measure we converge to measures, this hook arrow. If for every function in the dual, so LP prime, I have that when I evaluate this guy against the dual, they converge towards each other. For P equals infinity, there's actually the same notion, this notion of if I integrate against L1 functions, I converge. But we call it weak star convergence because this weak convergence means something very specific in functional analysis. So when you see weak star convergence, it's usually applied to things for P equals infinity. Okay, so this is just a definition. It's just helpful to know on some problems, just in case you need the actual definition. But when it boils down to actually showing convergence about these things, you'll just be looking at, you fix a function G, I integrate my sequence against G and try and figure out its limit, and then make that somehow independent of G. Okay. Great. Well, the great thing about weak convergence, it gives you compactness in some sense. So this is a corollary of what's called the Banach-Aloglu theorem. But for P being between 1 and infinity, if I take a bounded sequence in LP, so in some sense, if I view LP of RD as being this box, and what I'm saying is, okay, there is some circle in LP where this radius is going to be the sup in N of Fn in LP. Right, so I'm working on a closed ball in this function space. Then I know that for any sequence of points, right, I can find a limiting point. So it's like compact in LP, but it's not compact in the norm topology. It's compact with respect to the weak topology. So I know that there exists a sequence, subsequence, Fnk, and a limiting F, which is still an LP, such that I get weak convergence to this function F. Right? Okay, and so this is useful if I want, I just have you give me a generic sequence, and I want to find some limit of it. Just to, does anybody know there's a lemma called like the subsequence lemma? You guys know this lemma? You heard about this?
Is that the one where a sequence converges if and only if every subsequence has to say convergent subsequence?
Yeah, it's yeah, I think it's useful to know actually, like in general. So let me show it to you. Okay, so I might add this to the notes. There's a thing I would like you guys to remember, which is called the subsequence lemma. So the setup is if I have a metric space, and I think this works for more general spaces, but let's just say like a metric space. I think it could go to topological space. I just don't want to say anything incorrect. Then a sequence xn, and going from 1 to infinity, converges to x in x if for every subsequence x n k, for k going from 1 to infinity, and this is like a subsequence of xn, x n k converges to x as k goes to infinity. Right? Let me think. No, sorry. This is not the statement. So if I have for every subsequence, I can find a further subsequence, which x, n, k, j. Bad notation. There exists such that x, n, k, j converges to x as j goes to infinity. So what this problem or this lemma says is often for these types of subsequence problems, I can reduce to, you just give me an arbitrary subsequence and I show it converges. If they all converge to the same thing, then I show that it actually converges without taking a subsequence. Does that make sense? So it's somehow, I'm allowed to reduce to subsequences in many scenarios. This might actually just be for, I want to say, sequential topological vector spaces. So like fairly general scenarios. Okay, that was just an aside. I might put that in the notes or not. Let's see, we've got 15 minutes. Okay. The next thing I want to define is convolution. So if you give me any two L1 functions, I can define somehow like a binary operation between two L1 functions. So it's not just the standard product. What it's defined as is I take my first function and I fix an x, so that's this x here, and then I move it around by y. So I shift it by y. And then I take this shifted version and integrate it against y, right? So there's a couple things you can check. I'll just write them as exercises. F star g equals g star f x. And F star g is an L1 for f g in L1. So these are just two nice properties. In general, you'll end up having a lot of you get a lot of extra things by defining convolution. For example, let's say you're working with a function which is not smooth. So you'll often see this thing of there's things like mollifiers. So on RD anyway, it looks like this. X and R. Where if I take an F and I convolute it with a phi epsilon, this guy is going to be actually smooth if phi is smooth. So what it gets you is it's called a mollification. So if I take a smooth thing and do this convolution operation, I get a smooth thing. No matter really how rough f is, I can still take derivatives and it makes sense. And the nice thing about these mollifiers is that if I take epsilon to 0 for this guy, they end up looking like functions which converge to a Dirac. So in general, I have f convoluted with phi epsilon converges to f of x as epsilon goes to 0. So this is how analysts or the PDE people end up using this. Okay. Great. So let's go to, okay. So here's another functional analytic thing. L2 is special in some sense. So L2, I should say in particular, 2 is special. 2 is special. Since 1/2 plus 1/2 equals 1. So what I'm saying is P prime equals P. So in some sense, the dual is the same space. And in the case, I'm in the realm of Hilbert spaces, and I can define an inner product. So I measure somehow the angle between 2 functions in L2 by defining this integral where I take f of x multiplied by g of x, and I take a bar. Right? Okay. And so do I have, oh, okay. As a corollary of just this definition in Holder's inequality, what I end up getting is if I look at this inner product on L2, I get that this is less than or equal to f L2 g and L2. So this is Cauchy-Schwarz. Okay, so if you end up doing quantum physics, you'll end up using Cauchy-Schwarz a lot. Okay, so this makes L2 a Hilbert space. Okay, I think there's one more definition I'll talk about, and then maybe we'll work on a problem. So this is a weak LP. So in general, weak LP is bigger than LP, right? And actually there's things which are in weak LP, but not in LP. So it's somehow a generalization that still cares about the LP norm in some sense. So the definition of weak LP is the following. So a measurable function f lies in weak LP if I take NP of f, which is defined to be, I take the supremum over all levels lambda, and I look at lambda to the p and measure the set where f is greater than lambda, right? And if this supremum is finite, I say, okay, NP of f is the LP norm of f. Okay, exercise.